Welcome to this webinar where we will look at the main connectivity solutions used in the ODN, Optical Distribution Network, which effectively comprises all the parts of the passive network outside of the data center or central office. The optical distribution network incorporates the physical elements that are required to build the fiber network. These include the optical fiber, trenches, ducts, and poles on which it is deployed, fiber enclosures, optical distribution frames, patch panels, splicing shelves, drop cables, and so on. The fiber connectivity solutions have a direct impact on the network's performance, stability, reliability, and cost. Additionally, it affects network maintenance, operations, expansion, restoration, and the rapid implementation of new services, ideally without disturbing the transmission in other active circuits. The four primary elements of a strong fiber cable management system provides storage and protection of fibers, splices, connections, passive optical components, and cables, fiber and cable routing paths with bend radius control, modular circuit separation to reduce transient losses in adjacent groups of optical circuits, and lastly, fiber and cable identification and accessibility. Executing these concepts correctly enable the network to realize its full competitive potential. Fiber connectivity products provide storage and protection, both physical and environmental, of the installed fibers, splices, connectors, and passive optical components. Every fiber throughout the network must be protected against accidental damage by technicians or by equipment handling. Fibers traversing from one piece of equipment to another must be routed with physical protection in mind, such as using splice closures that protect from outside disturbances. Without proper physical protection, fibers are susceptible to uncontrolled bends, which cause transient optical losses and damage that can critically affect network performance and reliability. The easiest way to increase fiber capacity is to add as many fibers and cables as possible in the equipment. This results in splice trays with more than 96 splices per tray. The drawback of such mass storage systems is that during an intervention by a maintenance crew, many fibers or cables will be touched, either intentionally or by accident. The probability of an uncontrolled fiber bend becomes high, resulting in rapid changes in attenuation, also called transient losses. The figure shows a typical transient loss recorded when an installer handles fibers. These are fast changes in attenuation up to 10 dB, with a duration from 1 millisecond to several seconds. The transient loss should be reduced to a level below 0.5 dB to avoid transmission errors or bit errors in an active optical circuit. In network locations that require frequent intervention, such as the access or optical distribution network ODN, it makes sense to separate the optical fiber circuits by storing the fibers on individual splice trays. This reduces the occurrence of transient optical losses in adjacent circuits. Circuit separation is defined and described by the international standards IEC 61756-11 and ITU-T L516. The following separation levels are defined. Single circuit SC specifies only the fibers of one customer per splice tray. Single ribbon SR specifies only one ribbon fiber per splice tray. Single element SE specifies all fibers from a cable element, for example a loose tube, per splice tray. And multi-element ME specifies fibers from multiple cable elements on one splice tray, also called mass storage trays. A fiber management system should allow modular combination of splice trays with the above-mentioned circuit separation levels. Depending on the application, the type of splice tray can be changed. For example, in a long-distance network where cable segments are spliced together in track joints and where closure re-entry is not expected, the SE and ME splice trays are typically used. In the distribution points of an access network where frequent re-entry is expected over the lifetime of the product, the SC and SE splice trays are usually used. Cable access and identification is another important element to good fiber cable management and refers to the accessibility of the installed fibers. As the number of fibers grows dramatically in both the distribution frame and the active equipment, cable access becomes an increasingly important issue for service providers. Using SC and SE circuit separation levels will help identify the correct fiber circuits. With huge amounts of data as well as revenue moving across the fibers, the ability for technicians to have quick, correct, and easy access is critical. When there are service level agreements in place, particularly for customers with high priority traffic, the last thing any service provider wants is service interruptions caused by mishandling one fiber to gain access to another. The accessibility of the fibers in the fiber cable management system can mean the difference between a network reconfiguration time of 20 minutes per fiber and one of over 90 minutes per fiber. Since accessibility is most critical during network reconfiguration operations, proper cable access directly impacts operational costs and network reliability. In order to specify a fiber optic product or network element in the ODN, it is important to select the correct operating service environment. Where will the product be installed? IEC EN 61753-1 provides a list of environmental categories for enclosures and components. For closures, Category C, Controlled, is for indoor applications. Category A, Aerial, is for outdoor aerial applications higher than 3 meters. Category G, Ground, is for outdoor ground level applications. Category S, Subterranean, is for below ground level applications. For components, Category C, Controlled, is for indoor applications. Category U, Uncontrolled, is for outdoor applications inside an enclosure. By selecting the environmental categories for enclosures, the minimum required tests and severities are automatically specified. For closures, the following performance standards describe the test requirements in detail. IEC 61753-111-7, Sealed Closures for Category A. IEC 61753-111-8, Sealed Closures for Category G. IEC 61753-111-9, Sealed Closures for Category S. The user is allowed to add additional tests or to increase the severities. IP-rated closures and connections follow the IP code or Ingress Protection Rating, also known as International Protection Rating, which outlines the degree of protection provided by enclosures and components. They also classify and rate the protection against solid objects, including human body parts like fingers, dust, and water. Published by the IEC, the rating's goal is to provide detailed information about specifications for waterproofing and more. IP rating consists of 2 or 3 numbers. When there is no protection rating with regards to one of the criteria, the number will be replaced with an X. The first set of numbers classifies the IP-rated level of protection from solid objects and hazardous parts. 0 signifies no protection against contact and ingress of objects. 1 signifies protection against objects greater than 50 millimeters, which is any large surface of the body such as the back of a hand, but no protection against deliberate contact with a body part. 2 is objects greater than 12.5 millimeters, which represents fingers or similar objects. 3 is objects greater than 2.5 millimeters, such as tools, thick wires, and so on. 4 is objects greater than 1 millimeter, such as most wires, screws, and so on. 5 signifies protection against dust. Ingress of dust is not entirely prevented, but it must not enter in sufficient quantity to interfere with the satisfactory operation of the equipment, so not complete protection against contact. 6 signifies dust tight, no ingress of dust, and complete protection against contact. The second set of numbers describes the IP-rated protection against water. 0 signifies not protected. 1 signifies dripping water. Dripping water, vertical falling drops shall have no harmful effect. 2 signifies dripping water when tilted up to 15 degrees. Vertically dripping water shall have no harmful effect when the enclosure is tilted at an angle up to 15 degrees from its normal position. 3 signifies spraying water. Water falling as a spray at any angle up to 60 degrees from the vertical shall have no harmful effect. 4 signifies splashing water. Water splashing against the enclosure from any direction shall have no harmful effect. 5 signifies water jets. Water projected by a nozzle against the enclosure from any direction shall have no harmful effects. 6 signifies powerful water jets. Water projected in powerful jets against the enclosure from any direction shall have no harmful effects. 7 signifies immersion up to 1 meter. Ingress of water in harmful quantity shall not be possible when the enclosure is immersed in water under defined conditions of pressure and time. 8 signifies immersion beyond 1 meter. The equipment is suitable for continuous immersion in water under conditions which shall be specified by the manufacturer. In many cases, IP ratings are global and viewed as more important than the U.S. NEMA rating, which are only used in the USA. Although some ratings can be mapped to each other in some cases, there are different types of ratings that do not overlap. IP66, IP67, and IP68 ratings typically align with NEMA 4 and 4X compliance regulations, which are the most common requirements in the industry. In evaluating the connectivity needs of an FTTx architecture, a set of design requirements need to be defined describing how the system will work and in what network configuration. This includes, but is not limited to, assessing the number of fibers that may be needed for each connection point, the cable sizes and ducts to be installed in the feeder, distribution, and drop areas, what equipment, for example splitters, will be installed in buildings, distribution closures and/or cabinets, and what capacity of fibers and/or cables will be terminated within a certain cabinet or closure. There are many possible component choices for building FTTx networks. The most cost-effective option can only be determined by applying the different engineering rules and constraints for each approach to the actual geography of the region. Expanding outwards from the central office towards the subscriber, the key FTTx infrastructure elements are the feeder cable, which includes a large-size optical cable and supporting infrastructure, for example, ducting or poles. The Fiber Distribution Hub, or FDH, which is usually an easy-access underground or pole-mounted cable closure or external fiber cabinet, passive, no active equipment, with large fiber distribution capacity. The distribution cabling, which is medium-size optical cables and supporting infrastructure, for example, ducting or poles. Any secondary fiber access terminals, or FATs, which are small, easy-access underground or pole cable joint closures or external pedestal cabinets with medium or low fiber capacity and large drop cable capacity. Drop cabling, which is low fiber count cables to connect to the subscriber premises. And finally, any fiber in the SFU or MDU, which includes fiber entry devices, internal fiber cabling, and final termination unit. Let's discuss the main connectivity solution types in more detail. Feeder cables from the central office need to convert to smaller distribution cables. This is achieved at the first point of flexibility within the FTTx network and is generally known as the Local Concentration Point (LCP) or Fiber Distribution Hub (FDH). At this stage, the feeder cable fibers are separated and spliced into smaller groups for further routing via the outgoing distribution cables. The FDH unit may take the form of an underground or pole-mounted cable joint closure designed to handle a relatively high number of fibers and connecting splices. Alternatively, a street cabinet structure may be used. In either case, entry and further re-entry into an FDH is required to configure or reconfigure fibers or to carry out maintenance and conduct fiber testing. Street cabinets or distribution hubs accommodate passive and/or active equipment and can be custom configured for different applications to serve customer-specific needs. They are usually metal or plastic enclosures located to allow for relatively easy and rapid access to the fiber circuits and are capable of handling larger capacities than fiber joint closures. FDH cabinets are often used to store PON splitters, which also require flexible connectivity to subscriber-dedicated fibers. An important factor in the rollout of new networks is speed. Cabinets can be provided direct from the factory, pre-stubbed, tested, and terminated. The cable stub is run back to the next closure, offering a patch panel for simple plug-and-play connectivity, allowing faster installation and reduces the incidence of installation faults. This style of cabinet can be combined with plug-and-play PON splitters, which can be installed as and when required, without the need for further field splicing. In a typical FDH, both feeder and distribution connections can be made using multi-fiber push-on or MPO connectors or by splicing. Splicing adapter packs provide easy access to connections and splitters housed in the FDH, making troubleshooting and maintenance much easier for technicians. In keeping with craft friendliness, swing frame designs ensure easy technician access to the splitter chassis and splice trays or MPO adapters. In most instances, the distribution fibers from the FDH will need to be separated within the network before being connected to the subscriber. These are called fiber access terminals, FAT, and can be splice closures or hardened connector solutions. In the FAT, distribution cables are spliced to the individual fibers or fiber pairs of the drop cables, and these units are usually positioned at an optimum or strategic point within the network, enabling the drop cabling to be split out as close as possible to the majority of subscribers. These are typically an underground or pole-mounted cable joint closure with highly reliable sealing systems designed to withstand harsh conditions and containing a relatively small number of fibers and splices. Alternatively, if greater capacity is required, they could also be a small street pedestal. In either case, entry and additional re-entry into either of these will be required to configure or reconfigure fibers and to carry out maintenance and fiber testing. Hardened fiber solutions replace labor-intensive tasks done by technicians in the outside plant area with pre-connectorized and tested fiber terminals. We saw how these can be used for fiber indexing earlier in Lesson 6. There are many challenges and considerations when choosing the right drop cable solutions. In a typical FTTH project, network operators have to order, warehouse, and install multiple drop cable solutions. For outside applications, the drop cable solution has to withstand the rigors of extreme climate change, moisture, and harmful UV with fully compliant IEC and Telcordia-approved connectors. For indoor drop applications, the solution has to meet very different performance and labor requirements. Utilizing plug-and-play solutions like the Multiport Service Terminal or MST with hardened adapters eliminates the need for splicing at the fiber access terminal, which means the handholds or pedestals that store the terminals can be much smaller and therefore can reduce materials costs as well as simplify installation. MSTs are available with different lengths of OSP cable in various fiber configurations. Each MST tail returns to a centralized splicing point. Splicing crews, therefore, don't need to move around and require much less time than before to make the same number of splices. This allows the operator to deploy the network more quickly, both in terms of homes passed and homes connected. After the technician has secured the MST, pre-connectorized drop cables provide easy connectivity from the MST to the ONU at the subscriber's residence. Despite additional costs associated with adding connectors to fiber access terminals, the savings in cable placement, and the elimination of the need for splicing in sometimes difficult weather conditions on a pole or at a wall more than offset the added expense of the hardened connector system. Connectorized solutions also help offset upfront deployments where installing the drop to the premises can often be deferred until service is requested. They also ensure better overall network flexibility where the ease of mating connectors allows for fast service upgrades, changes, or network reconfigurations. Network flexibility is an important consideration, especially considering the inevitable changes to fiber technologies and applications that will occur in the coming years. Drop cabling forms the final external link to the subscriber and runs from the last FAT closure to the subscriber building. These drop cables usually have low-count fiber cores, but may include additional cores for backup or other reasons. For underground networks, the drop cabling could be via ducts or direct burial to achieve a single dig and install solution. Overhead drop cables will feed from a nearby pole and terminate at a chosen point on the building for onward routing to the termination unit. In either case, the cable assembly may be pre-terminated or pre-connectorized for rapid deployment and connection, as well as to minimize disruption during installation. Downtown landscapes are changing to incorporate entire communities of high-rise condominiums that offer a full range of services, including home office connections and large common areas that offer a variety of on-site retail outlets. In-home networking now means more than simple access to the Internet as homeowners demand multiple access points, remote audio or video entertainment controls, online access to pay utility bills, remote monitoring of home conditions, and many other services. These applications provide convenience for residents and also require flexibility and performance in the network infrastructure. Fiber to the home FTTH networks increasingly include multiple dwelling units MDUs such as apartments, condominiums, and townhouses as part of the network build. These environments are slightly different to the residential single-family unit SFU. When looking at the MDU environment, there are three essential network architectures: the high-rise MDU, the medium-rise MDU, and the low-rise MDU, including 2 to 3 story residential apartments. MDUs are linked from the central office either directly using a dedicated fiber for each customer or using splitters in enclosures in the field or building. The latter seems to get more traction as incumbent operators move into the deployment phase. The structure of the fiber optic network generally follows that of the existing copper infrastructure. In the route to the MDU, the gas and water supply channels running beneath the pavement are often nearing full capacity. Feeding in additional cables for the FTTH infrastructure may be difficult and often requires costly excavation work. If empty conduits or ducts are available, fiber optic cables can be blown into them over several hundred meters. Depending on priorities, a network operator can decide to use a connectorized, factory pre-terminated approach, splicing, or a combination of both. Connectors and optical splitter solutions guarantee faster provisioning and network upgrades. Splicing is used, for example, if a connection is difficult to reach or if a lack of space prevents the use of a cabinet with a cross-connect function. In existing sites, it may be best to go for a hybrid solution because most brownfield MDUs have a congested building infrastructure. This means that fiber optic cables are pre-terminated or connectorized at one end and spliced at the other, with the least accessible or difficult end pre-terminated and the other side spliced in the field. A typical medium MDU may comprise 3 to 8 stories, each of which has 2 to 4 units, whereas a high-rise MDU may have more than 10 floors. The ground floor is often used for commercial purposes, for example, a shop, restaurant, or bank. The units in the remaining stories function as flats or business spaces, which may be used as a doctor's surgery, offices, a law practice, and so on. MDUs represent a huge challenge for fiber optic cabling and necessitate an individual design to ensure that the FTTx network is able to scale the individual floors efficiently and reliably. Another consideration is whether the individual units have been purchased or rented, and therefore potentially subject to higher tenant turnover. A service provider's decisions for deployment in a particular neighborhood or for connecting to any particular building depends too on whether an existing infrastructure is to be updated or whether the building and its neighborhood are newly built. To anticipate and respond to the multitude of connection scenarios, flexible and adaptable solutions are essential. Solutions that can be easily adjusted to the requirements of a specific environment. FTTH requires fiber cable be run to each unit. The effort required to recable an MDU is technically laborious and demands that a number of legal issues be addressed. Directly supplying each unit with fiber optics depends on cable laying options available as well as unit ownership structures. The necessary agreements must be reached, something that may take some time and effort. These buildings sometimes have vertical and horizontal cable ducts, which already contain coaxial cables for cable networks or other supply lines like UTP cabling. Fiber optic cables may be fed through the cable ducts, and due to their physical properties, they can also be laid together with power supply cables. If there are no suitable cable ducts available, network engineers are confronted with the challenge of feeding the cabling into the separate floors without exorbitant cost and without leaving any visible traces of the installation behind. Disused chimney stacks are often employed for this purpose. In some older buildings, it may not be possible to lay fiber optic cables retroactively. This depends on the state of the respective building. Network operators should discuss the relevant options and procedures with the owner of the MDU at an early stage of the planning process. It is clear that for the above reasons, a flexible and dense cabling solution is a must for comfortably deploying FTTH in MDU environments. Another common type of MDU is that of residential facilities, student or group housing, retirement facilities, and so on. These are mostly 2 to 4 stories high and comprise of several apartments on each floor. In older residential facilities, relevant provisions for installing any new cabling, including fiber optic cables, are missing. This means that they present a great challenge to network engineers. Due to their complex layouts, supplying the individual building is often tricky, as excavation may be required outdoors, making such installations costly and demanding a great deal of time and effort. That completes this webinar. Thank you.